Today in class we talked about differentiability, but we first started by looking at functions that are not smooth polynomials. So in the first three graphs here, we have the absolute value function, a piecewise function consisting of a positive linear sloped line and a second positive linear sloped line connecting at -1. And in the third one, we have a piece of a parabola, which is y equals x squared when x is less than, I'll say less than or equal to 0. And the other function is another linear function for x greater than 0 with a negative slope for that line. So I asked the students to first start by sketching a graph of the derivative function. Okay, so if we look at the first function, the absolute value, we know that the slope when x is greater than 0 is the slope of this positive linear function, and the slope is 1. So we're going to draw a horizontal line at y equals 1. If you look at the left-hand piece, that slope is -1. Again, a horizontal line at y equals -1. Now at 0, we can't have both of those points being values, otherwise this derivative would not be a function. We're actually going to learn that the derivative at that point does not exist. Okay, let's keep going. So the red will be my f prime of x graphs. What is the slope on the second graph when x is less than 1, -1? The slope appears to be +2. There are some nice points on the graph to give me that indication. So we're going to put a horizontal line at y equals +2. The right-hand side of x equals -1 looks like we have a slope of up 1 and over 3, so a slope of 1/3. So beginning at -1 to the right, the slope of the curve is 1/3. Okay, let's look at the third graph. The parabola on the left is just like a y equals x squared graph, and if you were to draw the derivative of the x squared graph, you'd say the slope is 0 at the vertex, slopes are negative to the left and positive to the right, and you know that the degree of the quadratic gets reduced by 1 so that the derivative is a linear function. In our graph, we only have the left-hand piece of the parabola, so we're only going to get the positive sloped line to the left of 0. Okay. And I'm guessing on the slope there, we haven't learned that specific slope value yet, but there's your positive sloped line. Okay, what's the slope of the linear function on the right? It appears to be -1/2. So I'm going to put a horizontal line at -1/2. There will be an open circle at 0, 0, and an open circle at 0, -1/2. Okay, staying with these three functions, let's take a look at where, let's go back. Let's take a look at continuity. So f of x is f of x continuous at the specified x value? So let's justify our answers for this question. At x equals 0 on the f of x function, for number 1, is f of x continuous at x equals 0? Well, yes. So at x equals 0, f of x is continuous because, why? What do we need to state? We need to state that the f of 0 value is 0, that the limit as x approaches 0 from the left and the right on the function is also 0, and that the two are equal. If you just want to list both the function value exists and the limit values exist and write equals in between, you've covered your basis for continuity. If you want to say the function exists and the limit exists and they are both equal in words, you can do that too. Okay, let's take a look at question 2. Is our function continuous at x equals -1? At x equals -1, f of x is continuous because why? The limit as x approaches -1 on the function is 1. The function value at -1 is 1. And the two are equal. All right, same thing applies for number 3. So I'm just going to do a little copy and paste here. All right, now let's take a look at the third part of this question. Is the derivative function continuous for all x? Is the red graph continuous for all x? If no, state where it's not continuous. Well, it appears to me that at the x value in question, f prime of x is discontinuous at x equals 0. At x equals -1 for number 2, and at x equals 0 for number 3. What makes me say that? Well, you can look at the red graphs and say the two sides do not connect, right? Our limit from the left does not equal the limit from the right on the red graphs. All right, now I want you to think, what is happening on the function itself that's causing the derivative to not be continuous? Someone said in one class, the slope on the left side and the slope on the right side, there's an abrupt change where the slopes in your graph change, right? We're changing from a -1 slope to a +1 slope abruptly. In the second graph, we're changing from a +1/3 graph or +2 slope to a +1/3 slope abruptly. We just jump down there. Okay. What's happening on the function, though? Let's take a look. It kind of goes along with that idea of abrupt change in slope. The slope on the left is not equal to the slope on the right. So we could say the left-hand slope does not equal the right-hand slope. So f prime of 0 on the left side of 0 does not equal f prime of 0 on the right side of 0. A description of what's happening in each of these three scenarios is that this point on the graph is called a sharp point. Or it could be called a sharp corner. And in the case of the third graph, I'm going to just draw it out here again. You got this parabola going on, and then you got this linear line. This doesn't look like it's that sharp. I don't know if it could cut butter, but it doesn't matter. If there is an abrupt change in slope, you're going from one y value slope to another y value slope, then it's considered a sharp point, a sharp corner, or a cusp. So those are three words that describe what's happening on the function. All right, let's take a look at the next few graphs. This fourth graph is y equals x cubed. You guys should know the derivative of y equals x cubed pretty easily. We've done it a lot. It's going to be y equals x squared. Okay, now let's talk about the next two graphs. I want you to think about a horizontal tangent line to the function at different locations. So here, here, here. And as I get closer to 0, something's going to happen, okay? And then maybe out here, out here, out here, out here. Okay, so what are the slopes at this location over here? Well, they look like they're positive. In fact, this function is everywhere increasing, so the first derivative must be everywhere positive. But here we have small values, and as I get closer to 0, my slopes are getting steeper and steeper. This red dotted line, which you see here, doesn't show up very well on the Xeroxed copy, but this is called a vertical tangent. So what is the slope of a vertical line? We don't have a slope of a vertical line. It's undefined. So at the 0 on this graph, the slope is going to be undefined. All right, my derivative graph is going to look something like close to 0, getting larger and larger and larger as we approach x equals 0. On the right-hand side, we're going to start with very steep positive slopes, and the slopes are going to get smaller and smaller and smaller going to 0. Let's take a look at the third graph. Again, we have a vertical tangent. If you looked at this graph without me telling you that, you might not know that it has a vertical tangent, but I'm telling you, it does. Here we have negative small slopes, and the slopes are getting steeper and steeper and steeper. The slopes on the left are negative. Negative small to negative really big. Negative small, close to 0. Negative really big as we approach 0 from the left. On the right-hand side, well, the right-hand side is similar to the graph over here, the cube root graph. All right, so this one's going to be very steep positive slopes, getting closer to 0 on the right. Okay. All right, so in this story, I know you could tell me about continuity, but I'm going to jump to the idea of, are these functions differentiable? Okay, the x cubed is differentiable for sure because the polynomial is a smooth graph. It has no sharp points. It has no vertical tangents. It's all good to go. The next two graphs, f of x is not differentiable at x equals 0 because f of x has a vertical tangent. That goes for both of these graphs. All right, we could say f prime of x, or sorry, f prime of 0 from the left is positive infinity, and f prime of 0 from the right is also positive infinity. But in this case, we cannot say that our slope is positive infinity. We cannot say at 0 the slope is positive infinity. We have to say it does not exist. All right. There's one more item to wrap up here, and I don't think I'm going to be able to do it in 2 minutes. So I'm going to end this video and pick it up again, and then continue differentiability there. Stay tuned.